Assalamu alaikum, dear students. Today I welcome you to another lecture on this vector calculus. It will be now lecture number 15 that I am going to share with you. It is again on surface integrals because we have continued from lecture number 14. The surface integrals, there I have given you some brief, this introduction of surface integrals, how we find out the surface integrals, and I have also told you that how we use the integrals there by using the fundamental theorem of or fundamental definition of definite integral as the limit of sum. When the number of subdivision points or number of subsurfaces tend to infinity makes the area of each surface to 0, then that summation gives the integral, and that integral is called the surface integral. This much we discussed with you in lecture number 14. Now if you come to this lecture number 15, you should first revise lecture number 14 on surface integrals, or this is now we come to the evaluation of surface integrals, how we evaluate surface integrals. Actually, the best method or the convenient method for evaluation of the surface integrals is through the double integrals, and today I will tell you, I will share with you why we use the double integrals for evaluating the surface integrals. What is the logic behind it? What is the reason behind it that we use the surface integrals? I have already told you that some authors in different books, especially in engineering mathematics books, when they define the surface integral, they directly define it in terms of double integral over the region R. That is, when we project the given surface in some this plane in some region, then we evaluate it. It comes in the surface comes in the two-dimensional plane. Then there you have the double integral. You use the surface, evaluate the surface integrals in terms of double integral. Now actually today I want to tell you the how to evaluate or why we evaluate the surface integrals in terms of double integrals. Then it will be very easy to you to evaluate the surface integrals. So I have given the name to this evaluation of surface integrals. I will write here, I will start with this. To evaluate the surface integral, it is very convenient to express the surface integral as the double integral. Double integrals drawn through the orthogonal. It is orthogonal projection when we use orthogonal projection of closed surface closed surface S in any coordinate planes. But you will note, but this is possible only when any line perpendicular to the coordinate planes, any line perpendicular to the coordinate plane chosen meets the surface S in one point only. It should meet the surface S in one point when we draw the perpendicular from the coordinate planes. Let us see what is this, how we evaluate this. I will give you the let us consider this the rectangular axis, this three-dimensional rectangular axis, assuming this as x-axis, this is your y-axis, let this be z-axis. You know, along x-axis we have the unit vector, unit normal vector I. Along y-axis we have the unit normal vector j. Along this we have the unit normal vector k. This is your xy plane, okay. This is your yz plane. This is your zx plane. Then you consider any closed surface here in space. Let this be the closed surface in the space. Don't get confused that this closed surface at this time is in yz plane. It is in the space, and I am projecting this now in any coordinate plane. I will project in this on xy plane. Let me project this plane this way. I am projecting this. Okay, I project this plane in xy plane. Now just look, in lecture number 14 I told you how we find out the surface integral. Given the closed surface S, this is your closed surface S, this is your projection. You are projecting in the region R. We name this projection as region R where you project it. And what we do there, we have divided the surface into infinite number of subspaces, closed surface into infinite number of subspaces. Then we make the infinite number of subspaces infinite, and the area of each surface tends to 0, then that summation gives you what integral, known as surface integral. Now accordingly, let us take here, I will just tell you what we said in their lecture number 14. I told you that this surface element, I told you there, the surface element delta S surrounding, I am again reviewing just to recapitulate what we did in lecture number 14. The surface element delta S surrounding any point P is a vector. It is a vector in the direction of whose magnitude is delta S. It is a vector delta S, and is in the direction of outward normal n cap, so that we write this delta S as n cap into delta S. This is infinitesimal displacement, infinitude, this subspace, when area of each subspace tends to 0 when we make the infinite number of subdivisions. So accordingly, let us choose here an infinite subspace of area. This is your, assuming this is your subspace, this we take ds, this is ds, okay, infinitude of the subspaces. smallest of the subspaces. When delta S tends to 0, you get actually ds. Okay. Now we take this as assuming that this is the normal unit vector outward to the surface. Normal unit vector outward to the surface. Here you have this as, I take this as not this way, this is parallel to this, sorry. This is the normal, which is n is the normal unit vector to the surface S, and this is actually the normal unit vector to this xy plane, to this plane. Okay, I have represented it here. Now what we do is we project this in this region. Let us project this way. This is the projection. Here you get it is projection, assuming this is the projection. Well, we have projected this ds, the infinitude, very small, this subspace over the region R, and it is area is here ds. Naturally here it is area will not be now x into y. This is smallest also, if we take as dx dy. Okay, in other words, the projection of this area ds of the closed subspace S over the xy plane in region R is given by the area dx dy. Okay, so you have come to know how we evaluate this ds surface integral now in terms of the double integral. You will just come to know. Let me write here. Now we start. We write, let consider the closed surface S. Let capital R denotes the projection of surface S on capital R denotes the orthogonal projection. You should write here the word orthogonal. It is the orthogonal, denotes the orthogonal projection of surface S on xy plane. Okay, we took this as xy plane. Just look now, try to understand. Then we write, let n cap be the normal unit vector outward. It is outward to the surface S. Normal unit vector outward to the surface S. We choose this n. Let n be cos alpha I plus cos beta j plus cos gamma k. You know, when you write any unit vector along any direction, the coefficient of I, j and k represent direction cosines. We should write here where cos alpha, cos beta, cos gamma represent direction cosines of this unit vector n. Alpha is the angle which n makes with the x-axis, and beta with y-axis, gamma with z-axis. What is the angle? That means it makes the angle with the normal. When we define the angle between these two planes, as you know, it is the angle between their normals. Normal to this surface is n, and what is the normal to this surface? Normal to this plane, coordinate plane, it is this unit vector j. Similarly, when you talk of I is actually the normal unit vector or normal unit vector perpendicular to this yz plane. Similarly, this j is the normal unit vector to this xz plane. Remember this, you have done these things. I am just this recapitulating your memory. Well, we take n is equal to cos alpha, cos beta j, cos gamma k. Okay. Then we project this. We project ds on the xy plane given by its area dx dy. What is that? This means actually this implies dx dy is equal to projection of ds on xy plane. Actually, this is the projection of this. We project this part on this region, that gives you dx dy. I will just review your how you find out the projection from solid geometry. You know, just come to the solid geometry where you did in solid geometry. Suppose you have this area A, you project him somewhere here A dash. How you find out A dash is the projection of this area A? Assuming A dash the projection of this area A. How you find out this A dash? A dash is A times cos alpha or cos theta. This A dash I will write here. This A dash projection is A times A dash is A cos theta. What is this theta? Theta is the angle between the normal to this plane and the normal to this plane. Similarly, we will come now here. Come now, you have you project this. I have told you that it is infinitude of the surface. We project it here. Now dx dy is what? The projection of this ds. So we can write this dx dy is the projection of ds on xy plane. So according to that definition, A dash is equal to A cos theta. What you write? This implies your dx dy is ds cos gamma. Why cos gamma? Because gamma is the angle when alpha is the angle between n cap and x-axis. Gamma is the angle between n and k, where gamma is angle between normal unit vector outward to the surface and unit vector k cap. What is k cap? It is, we will say it is normal to xy plane. When it is normal to xy plane, it is also normal to this. Do you know? If a line is drawn perpendicular to any plane, then it remains perpendicular to all the lines which lie in the plane. It is the this geometrical axiom. If you draw a line perpendicular to any plane, any coordinate plane, then this line is perpendicular to all the lines which lie in the plane. So this is perpendicular. When it is perpendicular to this xy plane, so it remains also normal or perpendicular to this. So we write this cos gamma. This gamma is the angle between this n cap, normal unit vector outward to the surface, and this, it is the normal to xy plane on which you have projected this surface. Okay. Well, now how you find out this cos gamma? Now you have, now we can write what is n cap dot k cap. You can write as magnitude of n cap, magnitude of, by your formula, cos of the angle between them, it is cos gamma. That means you can write magnitude of n cap dot k cap, because this is 1, magnitude of unit vector 1, magnitude of unit vector 1, it is simply cos of gamma. Now using this, using second in first, when we use the second equation in first, what we get? Well, we have dx dy is ds cos gamma is magnitude of unit normal vector n dot k. So this means your ds is dx dy by magnitude of k. This is where s is projected, or you can say when s is projected on what? XY plane. When you projected the surface, closed surface on XY plane, you have ds is equal to dx dy by magnitude of the normal unit vector outward to the surface and dot the unit vector, unit normal to the given plane, coordinate plane to which you draw the projection. Okay. So accordingly you have come to know, now it is clear to you how it is convenient to evaluate the surface integral in terms of this double integral. Now you have what is the surface integral in terms of double integral. Hence surface integral can be expressed in terms of double integral as, what is this? Your surface integral over the surface S, it was f dot n ds. It is your previous definition that you did in your lecture number 14. There we have derived this one. We have derived this one by the definition of the definite integral as the limit of sum. I will again review your concept here. What we did here, we considered a closed surface and we divided that surface into infinite number of subsurfaces. Then we assumed that when this number of surfaces that we are dividing tends to infinity, then the limit of each surface is 0. When that limit exists, that is called the surface integral. Now this is your surface integral. You have seen that if we project the given surface, closed surface, orthogonally to the xy plane, we can evaluate this now in this way. It is double integral over R. What is this R? It is the region on which you have projected. Now it will vary. When you projected this, you have projected this on xy plane. If you projected this here, or if you projected this in this plane, yz plane, what happens? And I have already told you, don't get confused that it lies in the yz plane. No, it is in the space here. From space you are projecting in, say, xy plane. from space, sometimes you project it another plane, sometimes you project it another plane. I will give you the different values of ds accordingly. So let me write here, when we project it in xy plane, what is this double integral? It is f dot n. What is your ds now? It is this double integral. It is dx dy. You may put a question here, why double integral? Because you are in number one question to the query is that you are in the xy plane. For finding the area in the coordinate plane, you use double integral. You know the double integral concept. For finding out the volume, you use triple integral. For finding out the area in the coordinate plane, you use double integral. And for that, it is also clear, you get this ds in terms of dx dy. So it is your double integral over the region R. R is the region where you projected it, f dot and ds dy. This is the double integral evaluation of surface integral in terms of double integral when you project it in xy plane. Now we have different observations. Number one observation is what happens when we project in xy plane, yz plane, zx plane. On that I will write here. I will write here, we have now important observations. I will again write here coordinate plane, assuming this x, assume this as y-axis, assume this as z-axis. And along this we have unit vector I, unit normal vector j, it is unit vector k. Important observation is this: while projecting the given closed surface in any coordinate plane, we observe the following possibilities. These possibilities we will come across. Number one is this. Look here. Suppose this is the plane. If it lies in this plane, xy plane, sometimes you have it is a surface, two-sided surface. Sometimes it happens that surface lies in particular plane. If it lies in this plane, then its projection will be considered in the same plane. If it lies in plane, then projection is in this coordinate plane. If it lies here, then the projection is in this plane. Number one condition. Number second is it remains parallel in this way. It is parallel. Suppose at this time I am in the xy plane, my surface is here, so I will project in the xy plane. Okay, so we say if it is parallel to the xy plane like this, we will project it in xy plane. If it is parallel to this, we will project it in this plane. If it is parallel to this, we will project it. So this is second condition. One is the plane may lie in any coordinate plane, then its projection will be considered on that very plane. Number two is it may be parallel to any plane, then we project it in that plane to which it is parallel. And sometimes it is not lying in any plane and not parallel to any coordinate plane. Not lying, not parallel to any coordinate plane, जिसको हम कहते हैं टेढ़े मेढ़े रहता है ऐसे. Yes, what we do in that case? In that case, we can project it in any coordinate plane. Suppose it is here, I can project this surface here, I can project it here, I can project here, because in this case it is not lying in any surface, it is not parallel to any surface. So in that third case we can project it any plane. But in that case, how to find out n cap, that is the normal unit vector outward to the surface, it will differ. I am actually explaining you, you have come to know how to write I, j and k. It is very simple, I, j and k. Suppose if you project the this plane in here, in this, your normal unit vector to the plane will be I. Now the question is, what about n in that case? So I am going to explain this, you see. So while projecting the given closed surface in coordinate planes, we have the following possibilities. Number one possibility is, if the given surface S lies in any coordinate plane. If it lies in any coordinate plane, say it lies in xy plane or yz plane or zx plane, sometimes it is fully lying in the plane. If it lies in that plane, the surface will be projected in the same plane. यहाँ पे और हमने लिखा है, will be projected in the same plane. Number second, if the surface is parallel to any coordinate plane, then projection is considered to be on that plane to which it is parallel. That is, we project it on that very plane to which it is parallel. जिस प्लेन को ये पैरेलल है उसी को प्रोजेक्ट कीजिए, जिस प्लेन में ये लाई कर रहा है प्रोजेक्शन उसी में कंसिडर कीजिए, दो चीज़. Then you have third one, if it is neither lying in any plane nor is parallel to any coordinate plane, then what we do, then we project it any plane according to your convenience. Well, dear students, now see third condition, third possibility I am writing. If given surface neither lies in any plane nor is parallel to any plane, then we project it on any coordinate plane. When it is not parallel to any plane, not lies particularly in any plane, so we can project it any plane as we like. This is third. Now according to these three conditions, So accordingly, when surface is projected in different planes, the value of ds is different. It is not now always dx dy. The value of ds is different for different coordinate planes. Well, if you project here, if you project the surface on this yz plane, what is here ds? Note here ds value will be dy dz by magnitude of the normal unit vector outward to the surface dot what is the normal to this yz plane? Normal unit vector, it is I, it is n dot I. Okay, if you project it here in what xy plane, you have found its value. What is it? ds will be here dx dy by magnitude of unit vector n dot k, unit vector k, which is normal unit vector to this xy plane. If you project here, what is your ds? If you project in it, what is this? xz plane, ds will be dx dz by again normal unit vector n dot, what is normal to this? It is j. Remember this. Projecting the surface, coordinate surface, sorry, this closed surface in this plane, ds will take this value. If we project it in yz plane, ds will take this value for the double integral, evaluating the surface integral in terms of double integral. If we project here, ds will take value dx dz by n dot j. Now the question is how to find out this n cap, normal unit vector outward to the surface. Its value will also differ now. This is very important. This we will discuss now. I will not write this thing now here. I have explained this ds, why this ds is this. Okay, I will again tell you without writing now. Projecting the surface in xy plane, ds will take this value. We have worked out for this formula. We have this worked for this, and if it is in this plane, ds is this. If it is in this plane, ds, what does j stand for? It is normal. It is normal to this plane, normal unit vector. What does this I stand for? It is this normal unit vector to this plane. And what does this k stand for? Normal unit vector to this. Now we see right here how to find out. Now it is how to find out the value of n cap, which is normal unit vector outward to the surface. For this we will also discuss three cases. We have number one case. It is very simple now. If given surface is projected in xy plane, since take this is your xy plane, since unit vector k cap is normal unit vector to is normal unit vector to what? is unit vector to xy plane, we simply take here, take n cap is equal to k cap. So in this case, what is your ds, which was dx dy by magnitude of n cap dot k cap. This will be now ds is dx dy by magnitude of k cap dot k cap, which is 1. So in this case your ds is simply dx dy. It is simply dx dy when you project in this xy plane. Second point I want to discuss with you, if given surface is projected on yz plane, this is your yz plane, since I cap, this is your yz plane, I cap is unit normal vector to yz plane. So what does this mean? We take n cap is equal to I cap because it is the outward normal. We want outward normal. This is also outward normal. So in this case, what is your ds? Your ds is dy dz by I dot I. It is simply dy dz. And finally, third is when it is projected, yeah, we should not write here projected. I should write, you may get confused. If given surface parallel or lies, you should write like this, lies in yz plane. If the given surface is parallel or lies in yz plane, then you go this. When given surface lies or is parallel to zx plane, then you take n cap is equal to, what is your zx plane? This is your zx plane. This is the unit normal to the zx plane, that means j. So you take n cap is equal to j. So in this case, what is your ds? Zx plane, it is dx dz by magnitude of j dot j. It is dx dz. Therefore you will remember, if the given plane is parallel or lies in the xy plane, then we take ds as dx dy. If the given plane lies or is parallel to this plane, then we take ds directly dy dz. If the given plane lies here or is parallel to this plane, then we take ds dx dz. Now there is one more question. If given plane is neither lying in any plane nor parallel to the any plane, what is their n cap? We use here gradient formula. This is the fourth condition. So that is why I told you use lies or parallel. Now this is fourth very important one. If given surface is neither parallel nor lies in any coordinate plane, no doubt we project it that in any plane. but when initially the given surface, initially the given surface, जिसको हम कभी कहते हैं टेढ़ा मेढ़ा है, ये given surface is neither parallel to any coordinate plane nor lies fully in any coordinate plane, then what is n cap? Then we use neither nor. Then we use for finding out n cap as gradient of phi by magnitude of gradient of phi. You may put a question here. I will give you the reference. Refer directional derivatives and gradient there, because gradient gives normal vector. Gradient gives you normal vector. What is the unit normal vector? Along that, it is gradient of phi by magnitude of that. It is now unit normal vector to that surface which is neither lying in any plane nor is parallel to the any plane. We will use there this formula. Remember this. I have given you the reference there, directional derivatives, starting lectures, and gradient. We have told you there that gradient gives normal vector, because we use there Li plus mj plus nk dot something when we write down the normal. We have done that theorem on the directional derivatives. This is actually the working rule all how we evaluate this evaluation. Actually, those students who are doing the BTech with this mathematics, who are going to apply this surface integral, because they will get only the questions to evaluate, and those who are pursuing the degree courses and integrated courses, they may get a theorem here how we find out evaluate the surface integral in terms of the double integral. I have given all the things here, but for those students who are doing engineering mathematics, for this they have to only evaluate, but they must know how we find out this ds, how we convert ds, sometimes dx dy, sometimes dy dz dzx. This you must know. This I have given you today the complete representation, complete evaluation of this surface integral, how we evaluate surface integral in terms of the double integral. Now next will be now the application of this part, how we apply the surface integrals, just like we did in case of line integrals. Now we have surface integral. I will give you some problems we will solve together here on surface integrals, then we will go to volume integral. I hope you have understood this lecture, and you will revise at your places. Next we will meet very soon for this application of the surface integrals. Thank you very much. Thank you.